Okay, so let's do LC7 here. Okay, so again, you notice two things. We're approaching the origin, and the denominator is r to the fourth. Right? So let's convert this into polar just because it looks like it's got a lot of potential there. So let's take the limit as r approaches 0. And we've got, okay, well, r to the fourth on the bottom. In the top, we're going to have r to the fourth cosine squared theta sine squared theta. And then we're going to have r to the fourth cosine theta sine cubed theta. And then a denominator, that's x squared plus y squared quantity squared. So it's r squared squared, which is r to the fourth. And one way or the other, bad news or good news, choose to view it as you like, but all the r to the fourths cancel, and you end up with limit, as r approaches 0, of just a bunch of trig stuff. So we have this. And now you got to make an interpretation of what does this mean, right? And the thing is, we don't know that r. I mean, r is approaching 0, but that doesn't say anything about this expression. There's no r's in here, and it is bounded. Yeah, but what do we do with that? Yeah. So here's what you do with it. Remember that what we're doing is we're approaching the origin. Now, there's a bunch of different ways we can approach the origin. I could be sort of practical and sensible about it and approach along a straight line, or I could be a jerk and I could approach the origin like this, right? In which case theta is varying wildly. Or maybe I approach the origin from a different direction or what have you. And keep in mind, all I've got to do is find any two different paths where approaching along those two different paths gives me different values. And notice along this path here, theta is constant along that entire path. So on this path, whatever that theta is, along this path, I can plug that value of theta into here, and I'm taking a limit as r approaches 0 of, well, theta is a constant, so I'm taking a limit of a constant. And I'll just get this value for whatever that theta is for that line. Then I approach along this line, different theta, but it's still constant. Again, I'll get this kind of a value, but for a different theta. So the punchline is that because this expression depends on theta, the limit that I will get depends on which path I approach the origin along. Therefore, the limit does not exist. So you get different values along different paths, and that implies that the limit, the multivariable limit that I was interested in originally, does not exist. Didn't really have to parameterize these. I mean, I suppose you could, but I mean, you don't really have to, because the point is, as you're approaching along this path, theta is constant. That means that this isn't changing. So the limit of something that's not changing is just whatever that thing is. So this is the answer you get along that path. And it depends on theta. See, it's got thetas all over the place in there.
So that's why you know it's not.
You get that's right. You get different values along different paths. That's right.
I did. Like I plugged in the T and the MT stuff.
Yeah, you can do that too. Yeah, and you should have ended up with some function of m.
Yeah.
Yep. And so you make the exact same argument.
Okay.
Yeah, that's a perfectly fine way to do it. Let me just write that down. Just 2 seconds. So if you take the limit,
so whenever it's something dependent on, when it's dependent on something that's not in the original, like the x or the t or whatever it is, you know that it's going to change for every new value. Yeah,
that's right. That's right. If when you parameterize or convert to polar or what have you, if it depends on something other than what's approaching 0, and that, you know, so for example, like if you have r to the fourth here or something, then the answer is 0. That doesn't depend on theta. But this thing depends on theta. We have no control over theta. Theta could be who knows what. If it depends on something we have no control over, limit doesn't exist. That's right. So you're right. I mean, if you parameterize it, you know, by t comma mt and plug in and compute, you know, limit of f of t comma mt, and you do that out and you get some expression involving m's. It's going to have m's all over the place, right? Then yeah, that limit does not exist. Yeah, you had a question.
Yeah. Is it valid to say that if by just observing the function, it's a polynomial, like
Yeah.
the denominator is polynomial, so therefore it's continuous?
No, that's tempting, but it really doesn't work. So this, first of all, this is not a polynomial. This is a rational function, right? It's a polynomial divided by a polynomial. And if you look back at the rules for continuity, what you can conclude to be continuous, sure, polynomials, trig functions, other things, rational functions are all continuous where they are defined, right? And this expression here, that is not defined when you plug in 0, 0. And so critically, that you can't draw that conclusion. And in fact, we another way to say that same thing is when you look at fractions. Now you're right, polynomials are continuous, but what we have there is a fraction of polynomials, and we need for that denominator to not be 0. And tragically it is. So so that doesn't work. Yeah. Right. Let's see here. So that was LC7. Okay, let me stop this.